Hi, my name is Asira Saraswatula, and this is my report on Lab 5, Faraday's Law. The purpose of this lab is to apply the physical principle of Faraday's law to analyze and model the interactions between a falling bar magnet and a tube of aluminum foil. The physical principles exemplified in this lab are Faraday's law and Lenz's rule. Faraday's law states that there is a qualitative relationship between the rate of change of the magnetic field and the magnitude of the non-Coulomb electric field. Lenz's rule states that the non-Coulomb electric field would drive current in a direction to make a magnetic field that attempts to make the flux constant. In this experiment, I experimentally and computationally determined the amount of time it takes for a bar magnet to fall through an aluminum tube. The experimental average fall time is 1.702 seconds, while the calculated computational fall time is 1.487 seconds. The experimental setup is as shown to the left. I strung twine around an inner cardboard, allowing me to hang it up. Additionally, an aluminum tube was used since it would not magnetically attract to the bar magnet as a ferrous tube would. The measurements for the bar magnet and aluminum tube are shown in the center. I repeated the procedure of Lab 3 to recalculate the magnitude of the magnetic dipole moment, which is now 1.373867. The results of this experiment are shown to the right, indicating an average fall time of 1.702 seconds. This is greater than the time it takes for the bar magnet to fall in free space, which is 0.275 seconds. The computational model first initializes a graph and indicates physical constants and initial conditions as shown to the right. I then model the aluminum foil using the measured values of foil length, width, and tube radius to create a series of rings stacked along the y-axis. I also modeled a cylindrical bar magnet using the previously measured values of mass and magnitude of magnetic dipole moment in order to define the dipole points along the magnet's axis. I then created functions for the magnetic field and magnetic flux. The magnetic field function has magnitude of the magnetic dipole moment and position vector inputs, while the magnetic flux functions has magnet and ring object inputs. The next portion models the bar magnet falling through the aluminum tube using a while loop, which includes a time, velocity and position update, and a gravitational force, magnetic force, and a net force calculation, and a nested for loop that calculates for the change in flux over time, the current in the ring, the magnetic force from the tube on the magnet, and the magnetic field at each ring, the net force, and velocity. The final lines of code plot the velocity versus time graph within the while loop and prints the amount of time it takes for the magnet to fall through the aluminum tube. The velocity versus time graph shown here presents the total amount of time it takes for the bar magnet to fall through an aluminum tube, which is 1.487 seconds, which is less than the experimental value of 1.702 seconds. Several questions arose when interpreting the simulation. The first states that the red and blue current indicate current flow in opposite directions. Which color corresponds to clockwise and which to counterclockwise current, and how can this be told? Blue is counterclockwise and red is clockwise since there is a downward increasing change in flux, meaning that the induced current is flowing counterclockwise. The second question asks, what happens to the dynamics when the magnet is flipped around? If the magnet were flipped, the current would flow in the opposite direction. However, the force is acting on the magnet and the total time in tube is still the same. The third question asks how the total time in tube of the real-world system compares to that of the computational model, and how can the model be made more accurate. The total time in tube of the real-world system is longer than that calculated by the computational system. The computational system could be made more accurate if it took air resistance into account. The final question asks what the shape of the velocity versus time plot indicates about the forces acting on the bar magnet. The velocity instantly decreases in the plateaus for a long period of time and then decreases again. The plateau indicates that the bar magnet is not accelerating. Therefore, for a period of time, while in the tube, the gravitational and magnetic forces are balanced. We were also asked two concluding questions. The first question asks how reducing the resistivity of the conductor as close to zero affects the dynamics of the falling bar magnet. If the resistivity of the conductor approached zero, the induced current would increase, thereby increasing the magnetic force. Therefore, the magnet will fall slower. The second question asks what would happen to the ring currents in the model if there were holes or slots cut into the tube. If holes or slots were cut into the tube, the resistance will increase because there are fewer complete rings, thereby decreasing the induced current and magnetic force. This will cause the magnet to fall faster. To reiterate, the purpose of this lab was to apply the physical principle of Faraday's law to analyze and model the interactions between a falling bar magnet and a tube of aluminum foil. The physical principles pertinent to this lab are Faraday's law and Lenz's rule. By applying these principles to this experiment where I dropped a bar magnet down an aluminum tube, I discovered that the experimental average fall time is 1.702 seconds, which is much greater than if the bar magnet were in free fall at 0.275 seconds, since the bar magnet is experiencing a force from the aluminum tube. The computational model allows us to determine the direction of current flow to be counterclockwise and to calculate a computational fall time of 1.487 seconds, which is less than the experimental fall time since it doesn't account for air resistance. Thank you.